sharing, so you should.
I got it. I got it. Yep. Got
Amazing.
it. Okay. So the garbage collection we use today in Java wasn't always the case, but it's called a generational garbage collection algorithm. There've been multiple types of them. It actually came, I think the original one was created in Smalltalk. I remember reading one of the early papers on it that was in like 1993, 94 maybe. So it's a pretty old idea. The basic idea is you have kind of a tenuring system. So today's Java garbage collection has really three zones. It has Eden, which is where new objects go. It has survivor space, which is S0 and S1. And it has a tenured space, which is where long tenured objects who survive several cycles in survivor space go. So the first step is something goes into Eden. It then gets promoted to survivor space. Survivor space, it uses a copying collector. So survivor space will fill up S0, say, and once S0 is full, it'll copy all of the live objects to S1 and then wipe S0. And vice versa, once S1 gets full, it will copy everything back to S0 that's live, all looking for just the live objects, and then empty wipe the memory there. So I don't know how many times it goes back and forth, and maybe there's other tuning parameters for it, but you could think of it as like 3 or 4 generations. Once something survived a few minor GCs in survivor space, it then gets promoted to the tenured space, where it's much less frequently garbage collected. Now this model makes it really fast for new objects to be garbage collected, right? I think a lot of people who use Java coming from another language where you had to manage memory like C are like really concerned about creating a bunch of objects, but it turns out that Java's garbage collector is actually really fast because most objects will be born and die in Eden or survivor space and never get to tenured space, which is going to be more expensive to garbage collect than much larger space. So what the heap setting dash X, capital X, MS, and dash capital X, MS do is they set the total size of Eden plus survivor space plus tenured space. You also have a perm space where metadata goes, and I think you could even allocate some fixed objects in perm space. There used to be a large space, so very large objects, like if you loaded a gigabyte image file or something like that, it wouldn't, you know, it wouldn't blow your Eden size. I'm not sure what they do currently with large objects, but there have been various protocols for dealing with them. Okay, makes sense? Any questions?
Yeah, so with this, do they actually copy, does it actually copy from one of these, I guess, sections to another? Or is it just like referencing it differently?
Yeah, so it does in survivor space. So S0, S1 is actually copied. It uses called a copying collector. And the other ones do mark and sweep. So what the other ones do in Eden, so it uses different garbage collection algorithms in terms of how it finds the garbage. In Eden and tenured space, what it's going to do, I think it's true of Eden. I know it's true of tenured space. It uses mark and sweep. So it goes through and it tags every object as to whether object reference really as to whether it's used or not. And then all the unused ones get swept into the garbage. And it doesn't touch the used ones. Versus if you're in S0 and you're going to get tagged as used, and then you're going to be physically copied to another memory location. Does that answer your question?
Yeah, perfect,
yeah.
Thanks.
Yeah. And at a high level, just think of this, you know, generational garbage collection means you have a young generation and you have an old generation. And that's kind of the key concept to it, right? And you can apply different garbage collection algorithms to components within those. Anything else? Question-wise? No. So this is actually from Oracle's documentation. So the maximum heap size is going to be the smaller of a quarter of the physical memory on your box, not what's available, but what's actually physically installed, or 1 gigabyte. This is, the rules for this have changed back and forth a lot. There used to be the notion of server or client Java, VM, and everything. But so more or less, the maximum default heap size is going to be about a gigabyte. And you can and often do need to override this with the -xmx option. That's probably the most common Java option set is -xmx with a corresponding size in gigabytes. Okay. When we started moving to 64-bit architectures, there's kind of a problem because 64-bit pointers take up a lot more space than 32-bit pointers. So Java created an optimization for this, which is to use compressed object pointers that are 32 bits when you have a smaller heap. Typically it's 32 gigabyte heap, but that's an approximate number. And recommendations are that you should probably not go beyond 31 gigabytes if you want to still utilize short pointers. Now, if you need to go larger, that's fine, but you're going to get large 64-bit pointers, and that's going to take up a certain amount of space just switching from 32 to 64. So there's actually an interesting article on the blog you could look at about why a 35 gigabyte heap is smaller in actual space than a 32 gigabyte heap in terms of usable space.
Is there a performance issue during that switch? And what happens if the heap has to grow and then shrink constantly between the 32 gigabyte roughly range?
Yeah, I don't think it would, good question. I don't know what the performance hit is. There probably is one. Try to think, it may be based upon, just thinking out loud, I'm guessing it may take the, you have to, if you want to use anything larger than 31, right, or anything larger than 1 gigabyte, you have to explicitly set it. So if you set -xmx to something larger than that, it's probably going to start out with large pointers to begin with. There probably won't be a switch because probably switching from short pointers to long pointers would be a very expensive operation. So there's been a ton of different garbage collection algorithms. The most common ones in Java 8 are parallel or concurrent mark and sweep, CMS. I thought CMS was the default in Java 8, but that may just have been what we used with Cassandra. But what I've been reading tells me that the parallel garbage collector is the default in Java 8. Both of these split the heap into 3 regions for Eden, survivor space, and tenured/old space. When you have to do a full GC, it does something called stop the world, where it really stops all the threads from running while it's doing a full GC. And this can become noticeable. And it gets particularly noticeable when your heaps get larger, quote larger, around 8 gigabytes, maybe 12, but larger than 8 gigabytes with a parallel GC or a concurrent mark and sweep garbage collector often gets painful. And so, with servers getting larger, multi-core machines, Sun or Oracle at the time noticed this, and they decided to come up with a fix for it. And they came up with a new garbage collector called G1GC, which stands for Garbage First Garbage Collector. It's now the default in Java 9 to version 11. I think it's still the default in current versions of Java. They did backport to Java 8, so you can use it in Java 8. And in fact, it's often ideal to use in Java 8. When we talked with City, who was running Java 8, they were using G1GC. I've rarely seen a situation where switching to G1GC would not be probably a good thing to do. Generally speaking, G1GC doesn't have a stop the world pause, so that's really cool. It also works much better on large heaps. And what it does, and I'll show you in a second what this looks like, but it splits the heap into dozens and dozens of small little spaces. And the key thing is it requires very little tuning. So if you had a large heap and you were running with Java 8 using parallel or concurrent mark and sweep, you could spend days and weeks trying to tune GC to work better with a large heap. You could probably get it eventually to work better, but it would take a lot of work, and it would also be fragile to changes in system behavior, upgrades, things like that. So G1GC is just super nice because it's really kind of a hands-off garbage collector. You set the maximum memory size, and beyond that, you really don't have to set much. So this is an illustration, it's from an Oracle slide, of how G1GC splits those 3 spaces into lots of little ones. So instead of having one Eden, you get a bunch of small little Edens. Instead of having one survivor space, you get a bunch of small survivor spaces, and you get a bunch of tenured spaces as well. So what this means is, instead of stopping the world, meaning everything, you can just stop the threads that are using these small little parts while you do the major garbage collection on one of these fragmented memory areas. Questions
Right.
on this?
Doesn't this have an impact on memory fragmentation and performance at runtime?
How so? Why are you thinking that?
Well, if you have a big heap and you start fragmenting the memory across the whole heap, you will have to go back and fetch this at runtime, and it's a lot faster to read contiguous memory blocks than fragmented ones. Or is there a strategy to allocate memory blocks per thread?
No, I don't. Well, so threads can't really own memory blocks, to my knowledge. But you don't generally get into memory, aside from large objects, right? Large objects become a problem. Like, what if you have a larger object then? And these, I don't think these sizes have to be uniform. They can be different sizes.
Okay.
But they would tend to also stay, these things are not getting allocated and deallocated. They're allocated and then, I believe, remain fixed for the life of that Java process.
Okay.
And then objects come and go within it, right? Objects will get deallocated within it, and the memory space become free again. Somebody else have a question?
On that, would it not depend on the operating system's, I guess, allocation management, memory allocation management, because it's whether the operating system decides if it should be contiguous or.
Sure. So and that could be a reason you want to set the small size, right? So if one common thing to do is to set small size and max size to be the same, so that when the program starts up, it gets a contiguous block of 32 gigabytes of memory or something.
Yeah, but Java tries to do what the operating system does all over again internally.
Right, but physically, so to Kunal's point, if you start out with 1 gigabyte and then you grow by 1 gigabyte up to 31 gigabytes, let's say, which is your max, every time the operating systems had to allocate a new region of memory, and they may not be contiguous. Whereas if you set max size and min size to be 31 gigabytes to begin with, when the program starts up, it's going to ask the OS for 31 gigabytes of memory, which will more likely than not be contiguous.
Yeah, absolutely.
Yeah. Any other questions on this? No. So what's a memory leak in Java? Well, what they call a leak, which is not really a leak like we used to think of leaks, it's when you have objects that are still being referenced, but they're no longer really in use. A good example of this would be like connections that have gone away. If you connect to a database and you read some data and then you disconnect, if that connection is still referenced or the result sets are still referenced, you've put it in some log or you have an observer pattern that's held onto them, those objects can begin to accumulate. And since the garbage collector sees that there's a live reference to them, they'll never get garbage collected. So it doesn't happen that often actually compared to say C or C++ where leaks were like a real big problem. You know, Java's leaks can happen. They don't happen too often. It's, you know, again, a programming error when this happens. Somebody's not unreferencing objects when they should be unreferenced. And the symptoms are, you know, pretty clear. You typically, you might have a small leak, in which case it might not ever become a significant problem. But a big leak is going to cause, you know, constantly increasing memory usage because the objects are never going away. And your application will eventually get an out of memory error exception and the application will stop, right? We've all seen those. Now, sometimes when you get out of memory error, it just means you need more live memory than you allocated. You need to change -mx to be a larger number from 1 GB to 4 GB or something. Other times it could be indicative, once you change it to 4 and it crashes again, it could be indicative of a you know, a leak in the Java code. And what we'll be seeing with the visual VM is one way of trying to find those leaks. When you're looking at JV monitoring tools, there's a bunch of things out there. There's the Visual VM, which is a newer one. There's JConsole, which has been around a while. JProbe, I think, is a product from a company. I've heard really good things about the Eclipse memory analyzer. I've not used it. People are saying it's probably better than the Visual VM, but again, I don't have any personal experience with that. I will say the Visual VM was really simple to use. I know Miguel started using it too. We got City to
managed to install it and use it. So it's very, very simple to use.
Yeah, yeah. So it's got that benefit. There were some command line tools. So JMap and JHat were things that worked with really Java 7 and earlier. And as of Java 8, they've been deprecated. There's a new command line tool called JCommand, which kind of replaces some of those. We did use this at City to get to dump histograms, to do heap dumps. You can do a lot of things you can do in the Visual VM on the command line from JCommand. And it's already usually, I think it's installed as a part of most JDKs or JVMs. So for most customers, you can at least start with things like using JCommand and getting a class histogram, which we'll see in a minute what that is, or getting a heap dump. But possibly you can show them how to use the Visual VM and you can get all this stuff kind of in a more UI-centric way too that way. Any questions? Okay, that is the slideshow part of this. Let's go to, now that we've gone through that, let's go through the questions quickly. So Java's garbage collector manages both heap and stack memory automatically. Somebody want to tell me why that is false?
It only manages heap, not stack.
Exactly.
Stack doesn't need to be garbage collected. You wouldn't. You can't garbage collect the stack. It's
You can't,
last
yeah.
in, first out. Yeah.
Right. I mean, if you did, it would wreck your program. Exactly. So we just learned the default max heap size is 1 GB normally. It could be a quarter of the. So the answer really is it depends, right? If you only have a small amount of memory, if you're on a machine with 2 GB, you can get a quarter of available memory. So you're going to have half a gigabyte as a default max size. Object references are 64 bits in Java on a 64-bit CPU. Why is that false?
Depends on the heap size.
Yeah, as to whether you're using long pointers or short pointers. Part of garbage collection involves copying in-use memory from one zone to a fresh new zone. Why is this true?
The different aging zones.
Yeah, Survivor Space does this. Now, Tenured Space doesn't do this. I don't think Eden does this either. So it's not always used, but it is one of the techniques that's used in Survivor Space in the young generation. Okay, this is a trickier one maybe, but stop the world is a bigger problem when the heap is greater than 16 GB. I consider this false. Anybody want to hazard a guess to why?
Because if you have to do a garbage collection on a large amount of, I guess, data, then it will take longer. So it's more likely to stop your program for longer.
Yeah, but that would be indicated true, right? I think the right answer here is really false. And the right answer is you should be using G1GC if you got 16 gigabyte heap.
Trick question.
Trick question.
Okay.
don't use the parallel or G1 or CMS garbage collector. There's a fix for this, in other words, right? It's not a bigger problem. It just needs a different garbage collector. Unlike a C program, a leak in Java happens when you still have references to a now unused object in memory. Why is that true?
Because it's still referenced, it can't get rid of it,
Yeah,
even though it may not be used.
exactly. And that was it. Okay. I want to show you what we saw. So what was reported by Citi, and they were first getting this with Top, okay? And we had them install the Visual VM, and we saw this, okay? So this may be a little small, but what you can see here is, and this was in Kafka. So they had about 49 different plugins with Kafka. They were originally configured, I think, with about 16 gigabytes of memory. They bumped it up to 32 just because they thought maybe we'd need more, and that was the problem, but it wasn't the problem. And they kept most of the plugins disabled, but they found when they enabled the Privitar plugin, this sort of thing happened, and it would go from that's less than 1 gigabyte of memory, all the way up to 30, 32, something like that, right? And then garbage collection kicks in, it goes way back down again. It's just a sawtooth pattern. So, and the time scale here is about 20 minutes, right? So every minute to 90 seconds, they were seeing like this heat, the garbage that was being created was filling up the heap until it reached the threshold where a full GC would kick in. That would kick in, clear it all out, but the process would happen over and over and over again. And Miguel had the insight that it might be SSL being misconfigured, which was trying to reconnect over and over again. And in fact, that turned out to be true. So it wasn't really our code, but it was Kafka's method of connecting to a plugin. When it couldn't successfully communicate with it, it would just try it over and over and over again. And each one of those retries was creating a tremendous amount of garbage.
How do you get 30 gigabytes of garbage just from that?
Yeah, in 90 seconds, right? So as you might imagine, there actually is a bug. There's 2 bugs filed against open source Kafka related to this sort of stuff, but they've been open for years and nobody's been fixing them. So it's kind of worth knowing that if you don't configure your plugin correctly and it can't communicate, it could wreak havoc on your heap. So the other interesting thing here is this was not a fatal error, right? The ops team happened to notice this because they're using Top to see how much memory was in use, but it wasn't actually causing anything to fail. And it wasn't causing like a really high CPU or anything like that. So the symptom here was visible only if you looked at how the heap size was changing, or the in-use part of the heap and the garbage collection going on. Okay, with that said, I will just switch here to the Visual VM. So I've got it up. It's a product from Oracle, but it's free, works with OpenJDK, doesn't require the Oracle JVM or anything. And you can see I've got it working both locally with Tomcat. I'm running Publisher locally, and this is the Tomcat. It also will connect remotely, and I've got my VPN here connected to our demo VPN. I've got Tomcat running there together with the Privitar pod server. When you run remotely, you need to run the JSTAT-D daemon. JSTAT-D kind of acts as a proxy to let among other things, I guess the visual VM know what Java processes are running there and provide statistics to it. But looking at the overview page, there's only a couple tabs here. It's kind of nice that it gives you the JVM arguments. You can see all those, right? I don't know, system properties, I guess, is you know, the properties that you get in Java property files. It also tells you what version of the Java you're using. I run with version 11 because it works just fine, by the way. Engineer keeps asking if I've tested if I've tested it with version 9. I'm like, yeah, works fine. It gives you kind of an overview monitor. I don't find this super useful. You know, you might, but you know, it's okay. But you know, shows you how many classes are loaded. Java now didn't originally do this, but it will unload classes that are no longer used after a certain period of time. It has buttons here where you can perform a GC. And you can do a heap dump also. It also will show you a list of live threads. This is kind of cool. It doesn't usually mean a whole lot unless you have some wayward threads going on. Pretty much everything green is actively running, and all the other things that are different colors are either suspended, which is parked, or they're waiting on a timer, or they're waiting on I/O to happen, or they're waiting on some other monitor event. And then you also have the sampler, which is what we were mainly using here. And this shows you, if you click the memory part of it, which is what I did, it shows you a live tally of the number of objects you have and the number of bytes they're taking up. So what you're seeing here, because things are normal and there's not any issues, it's not really all that useful to look at this, basically a histogram. It shows you the entire list of all objects allocated in memory. So once you go down farther, you'll start to see our stuff, right? But not that it's worth tracking, having, you know, I don't know, one object of a TCP IP connection loaded. Most of the small numbers of things are not that useful, but you can still see them if you want. And what's dominating the heap is raw bytes, probably I/O buffers, raw ints, Java object, which I don't understand what that is actually, and some basic algorithm classes like the tree maps and things like that. So if you did have a memory leak though, which was not the situation at City, we had a garbage collection problem, which is not the same as a memory leak. But if you did have a memory leak, this would probably be showing you at the very top the objects that were accumulating in memory. So if you're accumulating Sybase JDBC connections, or you're accumulating dead shopping carts in a web app or something like that, they would be showing up near the top here. It'd be probably pretty easy to find what was causing memory leak just by looking at the histogram. It does have per thread allocations too. To an earlier question, Java, I mean, I guess it tracks which thread created the object, but that thread does not own the object, right? Because it's allocated in a general pool of heap memory. But you can see which threads are doing the most allocation of memory of live objects. And then the profiler, I haven't used this. I think you can write some, oops, well, I don't know. I haven't used the profiler, so I'll stop poking around with it. But mainly it's useful just for, you know, you can look at the threads, you can look at the memory histogram, which is great, and you can do simple heap dumps. Any questions?
No, looks great.
Okay.
Have you used this to look at distributed Java programs like Spark and such?
I have not, no. You can, so you can connect remotely. So you could, it would be, look, I can actually look at, let's look at the remote Tomcat here. I don't have JMX running, so it's not going to, ooh, okay. It can't do, unless I enabled JMX, and I tried to, but it got very complicated, requiring an SSH tunnel and stuff like that. So I gave up. But so I could definitely look at, you know, how Tomcat's running. I can also look at Pod. See how Pod's doing. And if I enable JMX, I could get the other you know, sampler screens as well. But right now it's failing because JMX is not enabled. So if you did have a Spark farm, you had, let's say, not instantaneous Spark execution engine spinning up, but you had fixed ones, then you could look through them the same way. Yeah.
I might do that. Since I'm writing a Spark application, I might have to do that.
Okay. It's probably easiest if you know, in a container, you figure out how to enable JMX, or if you're running them, especially if you're running them on the same instance. All I had to do here was just run JStatD. It needs a little one-line config file too. Any other questions? Alrighty.